This one is about rates of radioactive decay, which is really like half-life. So radioactive materials essentially decay by half-life. And we talked very briefly about this in chapter 14, the first chapter of the semester, because it has to do with kinetics and how fast reactions happen. So radioactive decay specifically follows first order kinetics. So any of those first order laws will apply to radioactive decay. Which is why we really only talk about half-life with regards to first order, because that's really the only one that's relevant to us. Okay, so you might remember these equations way back from the beginning. This is a natural log relationship if it's first order, remember. So the natural log of, now I have n for like amount, but a is fine also. At a certain time over the initial amount equals negative kt, or we had it integrated in a different way as well. And t1/2, which is the symbol for half-life, equals 0.693 over k. So between these two equations, we can solve for k, plug k in over here and find like how much we will have after a specific amount of time, or how much time will pass to get to a specific amount. So it is first order. So you can see by this graph, right? Essentially what half-life is the amount of time it takes for a sample to decay by half. So after a specific, whatever the half-life is, say it's 50 years. After 50 years, I have half of what I started with. After another 50 years, I have half of that, and so on and so forth. So really you never get to zero, but essentially it just decays by half and by half and by half. And that's what radioactive decay is like. Okay, so N stands for the amount. You can use these two equations. Now, if you've done half-life before and you know the regular half-life equation, you can use that. That's totally fine. But I'm using these equations specifically to demonstrate that it goes with the kinetics section. Okay, so this is how fast the reaction happens. Okay, so this is how we date a lot of things. It's how we find how old things are that have radioactive material in them. I want to talk about carbon dating to begin with. So carbon dating is a very, very useful process we've used to figure out essentially how old things are. C14 is a radioactive isotope of carbon, right? And almost everything has carbon in it. All living things are carbon-based, at least on Earth. Excuse me. So carbon 14 is going to be present in any carbon sample. Now, not very much, because C14 is not very readily available, but all carbon has at least a very, very small amount of C14. So the reason C14 is useful is because its half-life is only 5,730 years. So it allows us to date things on like the thousands of years mark. So there's a couple of things that we have to like assume are true, which are essentially true, to actually date things with carbon 14. So first of all, so C14 it exists in the upper atmosphere. This is actually how it is produced. Essentially, if you've got a neutron that hits a nitrogen nucleus, we end up with some C14 nuclei. So this kind of shows the breakdown of the carbon isotopes. Most carbon is carbon 12. There's a little bit of carbon 13 and very, very small amounts of carbon 14. Okay, so we make a couple of assumptions in order to do this dating. We assume that the C14 levels have been stable for the past 50,000 years, which they probably have. Probably hasn't changed much. They probably have changed slightly, but not enough to actually affect the dating of things. And then our second assumption is that all living plants and animals have a stable amount of C14. Now that's just saying like, it's not like everybody has a gram of C14 or something like that. It's just like a ratio. The bigger the living animal, the more C14 they would have had. It is based on mass. Okay, so it's really like a ratio. We know the percentage of C14 in living things. Okay, so the thing that happens that allows us to actually date these is when an organism dies, then that C14 starts to decay. So living things have a constant amount, but when it dies is when the C14 starts to decay. So at the time of death is a normal amount of C14, and then as time goes on, we have less and less C14 in comparison to C12. So that's how we kind of date it. And so we compare those decayed C14 levels to those in living things. So if you were going to use our equations from before, so I'm looking at these equations, to figure out how old something is, the original amount of C14 would be like if it was living. And then the C14 amount after a specific amount of time would be while it's dead. So we will use those equations. So we can essentially date anything between 150,000 years using carbon-14 as long as it has carbon present in it. So that's how we dated a lot of these substances. Essentially, you might be familiar with some of these, like the Dead Sea Scrolls, sequoia trees we were able to date. It helps us figure out a lot of what was going on in the universe at specific times, or not the universe, sorry, on Earth at specific times. Okay, so how do we use this method if I gave you a problem? Well, I've got a wooden artifact. The reason I told you that is because wood does have carbon-14 because it would have come from a tree that was living. We're going to date it using C14 dating methods. So if the test results yield a C14 rate of 9.85 disintegrations per second. So like I tested it, and this is how much radioactive decay is currently being produced. Then how old is it? We know the half-life of C14 is 5,730 years, and the C14 rate for living objects. So a living object gives off 15.3 disintegrations per second. So you can see it has decreased for the amount of time that it's been done. Okay, so this would be my radiation that it's giving off now as after time has passed, and this would be the original. So while it's living is the original. So I just plug that into my equation. So it'd be 9.85 over 13.5 equals negative KT. We're trying to figure out how old, so the time. So I do need K, so I use this equation to calculate K. I get that K is 1.21 times 10 to the negative fourth. That is per year. So if this was in years, this is also going to be in years. Plug that in and I get 3,640 years. Now, anytime you do one of these problems, make sure your answer makes sense, okay? So 3,640 years, does that make sense? Well, if it starts with 15.3, after one half-life, it would be about half that. So like what, 7.6-ish? And we're not quite that far. So it hasn't undergone an entire half-life. So it's not going to be 5,000 years old. And it's not, I'm getting close to that at 9.85. So 3,640 years is an answer that makes sense. It's not quite undergone a full half-life, but it's somewhere in between. Okay, now we can also use other substances for radioactive dating, not just carbon, because not everything has carbon in it, especially rocks. And rocks have been around a lot longer than living organisms. So we use uranium-238 to figure out how old rocks are. And that tells us a lot about how the Earth formations happened essentially. So we compare what we do for this one. Instead of carbon-14, we use U-238 because most rocks contain U-238 at their formation to lead-206. So this is what it decays into, is lead-206. Okay. So if I have a rock and it has 0.257 milligrams of lead-206 for every 1 milligram of U-238 in the sample. So like percentage wise, it's like 25.7% lead instead of uranium. Okay, how old is this rock? And I give you the half-life of uranium is 4.5 times 10 to the 9th years. So uranium's half-life is crazy long, which means we can date things that are a lot older than what we could with carbon dating. Now, I gave you masses this time instead of disintegrations, and we can't really use masses of different things in order to figure out how old they are. So we have to be able to compare the same amount of things. Like in the previous problem, we compared carbon-14 to carbon-14. If we're comparing lead and uranium, well, those have different masses. So what you need to do, this is our strategy, that's a strategy, is convert the lead amount into uranium so you can compare the original amount of uranium to the new amount of uranium. Okay, so this is how you do it. Simple dimensional analysis problem. I have in my sample 0.257 milligrams of lead. I just left it in milligrams. Convert to moles. So I did 206 grams. Notice I did not pull the number off of the periodic table. And that is because lead 206 has a mass of 206. It's a specific isotope. It's not an average sample from the periodic table. Okay, so 206 to 1 mole. 1 mole of lead comes from 1 mole of uranium. That's always 1 to 1. Essentially 1 particle of uranium turns into 1 particle of lead. And then 1 mole of uranium was 238. Again, not the number from the periodic table, but the specific number of the isotope I'm talking about. Okay, so I got 0.297 milligrams of uranium. What that number is how much uranium has turned into lead. Okay, at the time we're at now, that's how much uranium had been converted. right? Now it was originally uranium, right? And now it's lead. So originally, when this rock was formed, it had 0.297 milligrams of uranium plus the uranium that's still there. Okay, so the original amount of uranium is actually 1.27 milligrams of uranium. Currently, it has 1 milligram of uranium. Okay, so this is what it started with. This is where I'm at now. Notice it has not decayed by half, so it is not going to be 4.5 times 10 to the 9th years. But now that I have the amounts, I can plug those in and solve, and I get that it's 1.69 times 10 to the 9th years old. All right, so convert the lead into uranium, add that to the amount there is now. So we have the original amount of uranium, the full amount of uranium, and then compare that to what we have now. Okay,